Yannis, can you confirm that my audio works? Okay, so I think we can start then today. So welcome everyone. My name is Joris van der Vondel. I'm working at the QSP, which is the Quantum Solid State Physics section of the Department of Physics, our department, let's say. And I all welcome you here. So let's start with the official procedure. So, dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. I hereby formally open this session and I welcome you all to the public defense of Mr. Yannis Alexandros Argyriou Tsikrikonis. Mr. Yannis Alexandros Argyriou Tsikrikonis has presented to the faculty his PhD thesis on the topic Calibration of the MIRI instrument on board the James Webb Space Telescope and MIRI exoplanet spectroscopy, in partial fulfillment of the requirements for the degree of PhD in science, astronomy, and astrophysics. He shall now publicly defend his PhD thesis. Mr. Yannis Alexandros Argyriou Tsikrikonis, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. So I now give you the floor to Mr. Yannis Alexandros Argyriou Tsikrikonis. The floor is yours.
Thank you very much. I hope saying my name does not count in the total amount of time I have for my presentation. Hi, everybody. As was mentioned, my PhD work is quite instrumentation heavy, but I guess you could say that for the last 4 years, I've been tinkering away in a sandbox on the shoulder of giants. Let me share my screen. All right, hopefully you can see the slides. So I'll start by disassembling a bit the topic of my PhD. I have done so in 3 parts. So first I'll be introducing the James Webb Space Telescope and the main science themes that are covered in this mission. Secondly, I'll be talking about the MIRI infrared instrument and more specifically describe the technical specification of this one. And then thirdly, I'll talk about my work on MIRI calibration. So first, talk about the James Webb Space Telescope. This is a collaborative mission between NASA, the European Space Agency, and the Canadian Space Agency. And on the right here, you can see a photo of a full-scale model of JWST behind the JWST team at the Goddard Space Flight Center in the US. Of course, to do infrared measurements, doing so from the ground is a bit difficult because the atmosphere of the Earth absorbs most of the infrared radiation coming from space. Additionally, the thermal background makes so that the measurements are made more difficult in the infrared. And so for that reason, we need to send James Webb into space. In this slide, I show the distance of where the Webb Space Telescope will be placed with respect to the Earth. On the left-hand side, you can see the Hubble Space Telescope, which was the previous flagship mission of NASA, in a low Earth orbit. And the James Webb Space Telescope will actually be placed at a distance of approximately 4 times the distance between the Earth and the Moon, around the so-called L2 Lagrangian point. On the bottom plot, you can see the location of this one. And the advantage of this orbit is that actually the James Webb will be orbiting around the Sun with the same period as the Earth. And this has the nice advantage that it allows to always point the sun shield of the telescope towards the Sun. What is the sun shield's main focus or use? It is to basically block the intense radiation of the Sun from reaching the science instruments and the mirrors. So the sun shield, as you can see on this slide, will be basically dividing the environment into 2 sides. One hot side with the radiation of the Sun being blocked by the sun shield, where the temperature will be reaching a whopping 85 degrees Celsius. And on the cold side, the temperature will be down to minus 233 degrees Celsius, which, as you can imagine, is really cold. So what will be the main science themes covered by James Webb? First of all, James Webb will be looking at a multitude of galaxies and trying to answer questions in galaxy formation and evolution. In this slide, I show an image of the Andromeda galaxy taken with the Spitzer Space Telescope. And this galaxy is the nearest one to the Milky Way, and eventually in a few billion years will actually collide with a Milky Way galaxy. So pack your bags. The second science theme that James Webb will tackle is the birth of stars and protoplanetary systems. So as I mentioned, we'll be taking measurements in the infrared. And in this slide, I show you a difference between taking an image of the Carina Nebula in the visible on the left-hand side, visible wavelength range, and in the infrared. And so as you can see, the gas that is non-transparent in the visible wavelength range becomes transparent in the infrared, which allows us to observe a lot more stars and also the dust emitting from a lot of these sources. Thirdly, JWST will tackle planet formation and the origin of life. And on this slide, you can see on the left an illustration of a so-called protoplanetary disk, where the material, including the gas and the dust in the solar system, combines in certain orbits, where you can see these as dark rings, where usually we expect to find exoplanets. On the right-hand side, I show what happens when light from a host star traverses an exoplanet atmosphere. And depending on whether this exoplanet atmosphere contains clouds or not, you can actually see in the resulting spectra absorption features which result from the photons interacting with the molecules in these atmospheres. Fourthly, JWST will answer questions about the early universe. And what I try to represent in this slide are two main points. Firstly, the sensitivity of ground-based observatories is limited, because of the atmosphere, and secondly, because of how far they can observe in the visible. And the Hubble Space Telescope and the James Webb Space Telescope are actually better suited to observe further into space. And as you may know, photons travel from space to reach us. So the further back we look, the further in time we are looking. Because of the expansion of the universe, photons that travel a long distance to reach us actually get redshifted. And so photons that were once peaking in intensity in the infrared, in the visible part of the spectrum, will actually peak in the infrared when observed with James Webb. So one of the main features of the JWST is its primary mirror. This one has a size of 6.5 meters in diameter, and it's bigger than its predecessor, the Hubble Space Telescope, which had a primary mirror of 2.4 meters in diameter. In this next slide, I show the impact of having a larger primary aperture and also the impact of pixel spatial size. As you can see, over the years, different missions have included apertures of larger and larger relative ratio. And so both of these images show the Whirlpool Galaxy, or M51 as it's called. And so you can see that with the infrared astronomical satellite, with its 57 centimeters, the galaxy was barely resolved, while with larger apertures, over time we were able to better and better observe this galaxy and acquire more information in the process. Now I'll be touching upon the mid-infrared instrument. So the JWST mid-infrared instrument, also called MIRI, will be performing in different observing modes. This includes imaging, coronagraphy, low-resolution spectroscopy, and medium-resolution spectroscopy. And I show this on the left-hand picture. So the imager will actually cover the largest field of view of MIRI, and the other parts will actually cover smaller fields of view. The MRS has a small field of view here on the top right, and you can see that it will cover different wavelength channels of the MRS will cover a different field of view. So overall, the wavelength range will be spanning the 5 micron to 28 micron range. And to perform its science, MIRI will be using 3 detectors, one for the imager module, which covers the imager, the coronagraphs, and the low-resolution spectrometer, and 2 detectors, so-called short wavelength detector and long wavelength detector, for the MRS. So keen observers will have seen that even though I'm talking about a medium-resolution spectrometer, aka the MRS, I show here a 2D field of view, which is not very common, as most spectrometers actually produce 1D spectra at their output. So why is this? Actually, the mid-infrared, the medium resolution spectrometer is an integral field spectrometer. What does that mean? Using a set of optics, we're able to take an input scene observed with the James Webb Space Telescope and actually slice it into several pieces. So as shown here in the second step, the starting field of view image gets split into 6 segments. And then each one of these segments is dispersed in wavelength. And so we get the spatial information at different wavelengths, and then using computer reconstruction algorithms, we're able to reconstruct the original scene with the 2D spatial information at different wavelengths. We can then collapse these different wavelengths to regain the original image. And additionally, the extra perk is that we can get a 1D spectrum for each spaxel or spatial position in our image. MIRI specifically will be using 4 of these integral field units, and each one of these field units will actually cover a different wavelength range, as I denote here on the side. So 2 of these units will project their light on the short wavelength detector, and 2 of them will project their light on the long wavelength detector. And I show this in the next image. So on the top here, you can see, as before, the process by which imaging slicing optics spread the light into different parts of the detector. And then with our Echelle gratings, we're able to gain information on the wavelength. If on the bottom side here, you show, I showed the resulting image that you would get based on this process. And this is for extended source illumination. So we basically flood illuminate our detectors. So what is important to realize here is that each one of these pixels has 3 corresponding coordinates, 2 spatial coordinates and 1 spectral coordinate. The spatial information is contained in the horizontal direction. The spectral information is contained in the vertical direction. This exact same principle applies to the long wavelength channels, where you can see that the difference is that we have a smaller number of slices. One important aspect of the MIRI architecture overall is specifically its detector architecture. So this will pop up time and again in the next part of my talk, so I'll cover it here. So the way the MIRI detectors are stratified basically includes a anti-reflection coating at the very top, which basically means that light coming from the vacuum environment is we don't reflect a large part of the light coming into the silicon substrate. The silicon substrate is the bulkiest part of the detectors, and we also have a buried contact, an arsenic-doped infrared active layer, and a blocking layer. After these, you reach the pixel metallization. So the process by which a detection happens in the MIRI detectors is that the photon comes in through the top of the detector, also known as the backside of the detector. Then it crosses through the silicon substrate, and inside the arsenic-doped infrared active layer, it photoexcites an electron of the arsenic impurity. And this electron then is accelerated to the pixel metallization thanks to a electric potential between the buried contact and the pixels. This is how we essentially detect photons with MIRI. Another important aspect I need to touch upon here is actually twofold, and both of them apply to the detectors. First of all, the reflectance of the anti-reflection coating is not 0. What does that mean? That means that as a function of wavelength, shown here on the x-axis, a different fraction of the light will enter the detector and a different fraction will be reflected back. That is an aspect that will come again later. Secondly, the absorption in the infrared active layer actually depends on wavelength. So the arsenic impurities give a certain absorption coefficient. And so as I show here with a dashed black line, at 5 microns, assuming a first pass, so the photons come through the top and go once through the infrared active layer, in a first pass, we only expect 17% of the light to be absorbed. If not all of it is absorbed, it will be reflected at the pixel metallization, and then with a second pass, an additional fraction of that light will be absorbed. The remaining light will go back towards the anti-reflection coating, and part of it will be reflected again towards the pixels, and part of it will escape the detector. This is an important aspect of MIRI and other infrared instruments in general. Now I'll talk about my work on MIRI calibration, but first I need to clarify that calibration work on MIRI did not start with my PhD by any means. It actually started in 2008, where they had the verification model of MIRI tested at the Rutherford Appleton laboratory in the UK. And since then, we have had multiple test campaigns to characterize MIRI. And so this work is based on a lot of effort of a lot of people through the years. And so this needed to be clearly stated. So despite all of these efforts, there were still outstanding questions in MIRI calibration at the time when I started my PhD. And I'll be covering 4 of them here in this talk. So the first one is, why is the MRS point spread function broader than expected, below 8 microns? The second one is, what is the origin of the MRS stray light? Third one is, why are MRS point source fringes different from extended source fringes? And the fourth one is, what is the origin of the low frequency modulation in MRS spectrum? And I'll be trying to convince you that at least the partial answer for all of these effects is photon scattering inside the MIRI detectors. So first, to touch upon the MRS PSF. On the top left corner, I show the image that you've seen before when we flood illuminate the detectors. But of course, for the point spread function, we are essentially talking about a point source in the sky illuminating our detectors. So in the left image, with the faded gray, you can see the same slices as were shown for the extended source. And with the white stripes, I show the point source illumination of the detector. So if you take a detector row and you plot that on the right with the x pixel as a function of signal, for the MRS, we measure signals in digital numbers. And for the flux, we measure it in digital numbers per second. And so you can see that different parts of the point source, similar to an extended source, are projected on different parts of the detector. So in the next slide, what I'm going to do is actually focus on the main peak here. And additionally, I'll be doing so for different detector rows and combining this information with what each pixel, which part of the sky each pixel sees. So this is shown here on the top plot, where prior to this work, based on the MRS optical model information that we had from MIRI, you can see that plotting each one of the pixel signal values that have been normalized based on the spectrum of the source actually yields a distribution of pixel signals that is very broad. And this should not be the case, mainly because the point source is singular in the field of view. So what you should basically be seeing is a single, very smooth distribution. So after calibrating for the fact that there is some discrepancy between the optical model and reality, so how the actual signal is projected on the detector, you can see the result of this in the bottom plot. So this results in a point spread function that is much sharper. And what that actually means, if you were to get some intuitive sense of this, is that if you were to collapse, as stated before, your information in wavelength, what the results you would get with the previous calibration, so the plot on the top-hand side, is in the case of the Andromeda galaxy that I've shared before, you would see that your image is blurred due to this effect. However, if you were to account for the spatial distortions that are introduced by the optics, you would get a much sharper image. And so this is an important step forward. So on this plot, I compare as a function of wavelength, the width of the point spread function, or how wide a point source appears on your detector. So this correlates to how sharp your image is. And so what I show with the diagonal dashed line is the diffraction limited model for MIRI, which gives you the width of your point spread function, assuming that this one is mainly dictated by the aperture size of your telescope. And with the horizontal line, I show the previous estimates of the width of the point spread function. And so based on these results, calibrating the spatial distortion, which was done in collaborations with my colleagues in Zurich, you can see that we are able to correct for a significant part of this unexpected broadening below 8 microns. However, there is still a remaining question about the residual broadening that we see above the diffraction limit. So to summarize, we find that calibrating the geometric distortion solution of the MRS as a function of wavelength drastically improves the PSF definition. However, there's still a discrepancy between the calibrated PSF width and the diffraction limited model. This involves the stray light discussion, and so I'll be continuing in the same breadth with the second science question. So MRS stray light appeared quite unexpectedly based on the MIRI models and all of the optics and the elements that were designed to ensure that stray light was kept to a minimum. So in this picture, I show you a different point source observation, and I would like to draw your attention to the right half of this image, where I show for one detector row the log 10 scale of the signal for a point source observation. In blue, you see the signal that we measure, and in orange, we basically project and scale our PSF model based on prior information. So based on how the optics work, we know that there should be no signal in the slices that surround the central peak. However, we see that there is quite some signal there. And if I were to do the same trick as I did before and plot just the central peak, you can see in this plot as a function of position in the sky and the normalized PSF that we see that for the empirical data, the wings have much more power than expected in the wings. And so this is actually something that has been observed before, and specifically it applies to the Spitzer Space Telescope infrared camera. So on the left-hand side, you can see an image of the theoretical point spread function. And in the middle panel, I show what was observed with Spitzer, where you can see a bright cruciform pattern overlapping the, as it were, the theoretical PSF. In the right plot, I show here a cross section of this detector image, where you see once again that there is a discrepancy between the theoretical PSF and the observed data. And so I argue, and in the paper where I'm a co-author by András Gaspar, that the photon scattering inside the detector actually means that because you are not absorbing all of the light in a first pass, part of this flux or part of these photons will actually enter at different locations on your detector. And that's how you spread the power that should be in your core of your PSF in the PSF wings. One way to also visualize this is to look at an extended source observation, where I show here on the top side an image that you've seen before, and I will take just a detector row through this image. And for an extended source observation, you see that we get several plateaus of signal as a function of row position, or column, I should say. And so because of this broader PSF and additional stray light, you can see that despite at these red points, by design, you should not be measuring signal here. We do see a significant amount of signal, and in this case, for this wavelength channel, it amounts to 20% of the total signal. And so how can you understand this a bit more intuitively? It is basically, if we were to just give a qualitative comparison, it is basically the same as having a much higher background, as shown here in the left-hand side, compared to having a lower background. And so, as you can imagine, this impacts your sensitivity. What I'm going to do in the next two plots is basically look at how, even though we did not expect to see signal on the outer parts of our images, how this signal compares to the wavelength information. And so in this plot, I show that as a function of wavelength, and for 3 different black body temperatures of our calibration source, the stray light behaves in a very consistent manner. Basically, it is high at 5 microns, and it basically decays all the way down to approximately 0, around 12 microns. And so I argue, once again, that this is related to the fact that we do not absorb all of the photons incoming into the infrared active layer, where at 5 microns, the absorbed intensity is around 30% after a double pass. But at 15 microns, we are basically absorbing all of the incoming photons. And so there are no more photons to scatter, that scatter inside the detector. And so to basically summarize, for the question of what is the origin of the MRS stray light, I argue that the photon scattering inside the detector arrays in the spatial direction produces the stray light and contributes to the broadening of the PSF below 10 microns. The full impact of this effect, of course, still needs to be modeled. The coherent reflections, on the other hand, of light inside the detector in the spectral direction produces the so-called MRS fringes. And so now I'll be touching upon these and what these are. So fringes have been quite a pain to deal with for a lot of infrared instruments. And I show here 2 examples. On the left-hand side, I show you the response function of the Infrared Space Observatory for the short wavelength spectrometer. And so you can see that depending on which wavelength you look at, the response of the detectors varies very rapidly. And so this is a manifestation of scattering inside the detector in the spectral direction. On the right-hand side, I show that even for the Hubble Space Telescope, and in particular the STIS data, be above around 0.7 microns, you once again get these intense fringes. And so what that means is that you can get this kind of manifestation even in the near infrared. And of course, you can imagine that for absorption features, as I mentioned before, these sort of high frequency modulation can impact your science drastically. In this presentation, I was going to talk about the difference between point source and extended source fringes. And so on the left-hand plot, I give you a qualitative idea of how we can extract spectra from our detector images by basically taking a column of pixels and plotting the wavelength information of each one of these pixels as a function of the signal. On the right-hand side, you can see for different spectral channels of the MRS, the information of a given by a black body source. So despite expecting to see a very smooth and, let's say, well-constrained signal, you can see that there's a large envelope surrounding what we expected to get as our flux. And so this envelope is produced by the internal scattering inside the detector, which produce coherent reflections of the photons. And so this envelope we usually correct with a static fringe flat for flood illumination. However, there remains a question of how does the fringing behave for point sources. And so if I were to focus on one spectral band, what I will be doing in the next slide is comparing a spectrum taken in an extended source image and then a spectrum taken at different locations of a point source image. So this slide is quite busy, but I'll try to break it down a bit. I focus here on just one trace on the detector, as you can see here on the bottom left. I take different lines across this point spread function, where these lines approximately follow constant positions in the field of view. So again, you can see how the optical distortions distort your the spread of your PSF at different wavelengths. On the above this image, I show the spatial distribution of the flux, i.e. the point spread function. And with the dashed lines, I'm showing you the equivalent extended source illumination of all of these pixels. So basically this is flat topped when you flood illuminate the pixels. On the right plot, I have normalized the fringe information for different parts of the extended source observation and point source observation. So you can see that the dotted fringes, which give you a high frequency modulation, basically stay consistent at different locations, at different pixels. However, the match between the point source fringes and the extended source fringes actually worsens the further away you go from the PSF center. And so we characterize this in two ways. First of all, we look at the depth from the unity line for the point source fringes. And then second of all, we look at the phase shift, the relative phase shift between the extended source fringes and the point source fringes. And so we found that doing so and linking the depth of the depth of the point source fringes to the location from the PSF peak, we found a smooth and continuous relation between these two quantities. So how depending on which part of the pixel is illuminated, but by which part of the PSF, you get a different fringe depth. And the same applies to the fringe phase, where we see that depending on which part of the PSF is sampled, the relative phase changes with respect to the extended source fringes. And so with these results, we were able to produce a more consistent fringe flat applicable to point sources. And I show here the optimized fringe flat now for, instead of an extended source, I show the fringe flat that would apply for a point source observation. And so you can see that we are able to model this effect much better, which improves also our spectroscopic accuracy. So to give a summary about this, basically the point and extended source fringes agree at the peak of the PSF due to the similar pixel illumination. However, the depth and the phase of the point source fringes in the PSF wings depend on the non-uniform illumination of the pixels. And one important aspect of this is that we find that this trend is reproducible across the MRS field of view. Lastly, I'll be touching upon the low frequency modulation that I've mentioned before. And once again, I show the same set of spectra as I did before. And I would like to attract your attention to the, as I mentioned, lower frequency information in the spectra. So the question for a long time was, what exactly is producing this low frequency variation, which varies from a small, like 2% variation to actually up to 5 to 10% variation of your spectral baseline. And a second question related to this is, why exactly do we see fringes at the wavelength above 15 microns? So the rationale for this question basically comes from the fact that, as I've stated before, after a double pass, you would not expect a large fraction of photons to still be reflecting coherently inside your detectors. What that means is that as you reach 18, 20, 22 microns, we would expect this fringing signature to disappear. However, we still see that it is present and actually impacts our data significantly. And so my work on this aspect was to basically try to understand this problem. And so I separate this into two cases, where I show here on the left-hand side what the traditional understanding of the MRS fringes was, where you can see that photons coming from the top pass through the infrared active layer and actually reflected on the pixel metallization and back and forth. So this explained the high frequency modulation that we saw in the data. And however, it could not explain the low frequency information that we saw. And so on the right-hand side, I show that we actually found concrete evidence that the buried contact inside the detectors is actually not as transparent as was thought before. And so it actually introduces a differential in refractive index between the silicon substrate and the infrared active layer, where due to the higher doping of the buried electrode, this introduces a larger change in the refractive index of this layer, this small layer here. And so what happens is that at low wavelengths, what you are seeing is essentially a beating between two fringes, between the top here, the anti-reflection coating and the buried contact, and a second fringe between the buried contact and the pixel metallization. At longer wavelengths, where most of the photons get absorbed in the infrared active layer, there is still coherent reflections happening between the anti-reflection coating and the buried electrode or buried contact. And that is what you see as the resulting fringes. So with that, I would like to conclude this presentation. My conclusions for this part was that we identified two causes for the unexpected broadening of the MRS PSF, which include the calibration of the optical distortion and the detector internal scattering. Secondly, we argue that what was previously reported as MRS stray light is a manifestation of detector internal scattering. Thirdly, the behavior of the point source fringes is found to be in line with the non-uniform illumination of the detector pixels across the PSF, something which was not considered before. And fourthly, we find that the detector buried contact has a significant impact on the MIRI detector optical behavior. Finally, for future work, we need to calibrate the MRS distortion solution across the field of view to ascertain that we are characterizing the MRS PSF model accurately. Secondly, we will update the PSF model to account for this detector internal scattering. Thirdly, we will develop a tool to produce a fringe flat based on an arbitrary scene illumination, since we know that how the fringes behave across the PSF, and we can combine this information to produce fringe flats based on arbitrary illumination of the detector. And then fourthly, we need to prepare all the necessary tools in preparation for JWST MIRI commissioning, which is slated to start at the end of this year. Fingers crossed. So with that, I would like to thank you for your attention, and I welcome any questions you may have.
Okay, thanks. So I'm back online. Thank you, Yannis, for keeping nicely in time. So before we go to the questioning, I will first introduce the members of the examination committee to everyone here. So we have, of course, Christopher Walkes, he's a supervisor, and Bart van den Busse, who is as well, let's say, the supervisor. They are both working at the Institute for Sterrenkunde. Then we have myself, Joris van der Vondel, from the same department, but the condensed matter physics. We have Professor Hugues Sana from the Institute for Sterrenkunde. We have Dr. Andrew Tkachenko from the Institute for Sterrenkunde, and we have Dr. Pierre Royer, also from the Institute for Sterrenkunde. And then from external board, let's say, members, we have Professor Alistair Glass from the Royal Observatory in Edinburgh. Welcome. And we have finally, let's say, Professor Bernhard Brandl from the Sterrenwacht Leiden. So, okay, let's start the questioning. And as it is the tradition, at least for the defenses I had, we start with the farthest from here, which is Professor Alistair Glass. The floor is yours.
Thanks very much, Joris. And first of all, can everyone hear me? Yeah? Can you hear me? Good. And thank you, Yannis. I thought that was a very entertaining summary of your thesis. Enjoyed it enormously. Very well presented. So just a couple of questions this time. First of all, I think just to set the context again for the wider audience, JWST and the MRS, we think are, if everything goes well, if the launch works well and the instrument works well, early next year, as you said, end of this year, early next year, we expect it to be able to make an observation of a compact target. So a star, a distant star, or a distant supernova exploding way off in the distant universe, thousands of times faster than can be achieved using existing ground-based observatories, or indeed the best historical space-based infrared observatory, which, let's say, Spitzer. So first of all, could you summarize why we expect, what are the features of JWST and MIRI that give us those big leaps in performance that we expect to see?
Right. Thank you for your question. So first of all, as I've stated at the start of the presentation, James Webb will have a much larger aperture compared to the Spitzer Space Telescope. So this will give us a much better, well, for a compact source, this should indeed give us a better resolution. And then secondly, we will be, I believe, with the sun shield, of course, this has reduced the thermal background tremendously. So this will improve the sensitivity of James Webb. And then thirdly, with the detectors, we will be the resolution with the shell gratings of the MIRI instrument will be able to resolve the wavelengths better than we've been able to before.
Okay, so can you think, for observation of a point source, you said that the PSF, the image is more compact, so you can resolve detail, that's true. But the other effect is that you're concentrating all the signal from the source into a very small region, but where you're looking at less of the background light. Do you happen to know how the sensitivity scales with the area, the collecting area?
So in terms of the collecting surface that we have, it's with the square of the collecting surface.
The square of what?
Of the size of the radius
of the diameter.
Yes. Yeah.
So it scales with the area. That's correct. Yeah. So sensitivity scales with area, and the time it takes to do anything interesting in astronomy goes as the square of the sensitivity. Yeah. So it's a big gain. A big gain. Okay. And in particular, the particular advantage we have with JWST compared to ground-based observatories. Well, two I can think of.
Yes. So first of all, there's the fact that the thermal background, of course, in ground-based observatories is much higher in the infrared. And secondly, we have
why is that? Why?
Why is the thermal background? Because in the infrared, you have a lot of sources producing, let's say, radiating in the infrared, and so that can result in a higher background.
Yeah, it's because they're warm.
Yeah. And then right. Yes. Put very simply. Yes. And then secondly is the fact that on the ground we have an atmosphere above our heads, and so this atmosphere produces turbulence, and so this impacts our sensitivity.
Turbulence, but the other thing about the atmosphere is it's warm. And it's opaque, but good.
Well, in the infrared, yes.
Yeah. Okay. Now I want to move on to a particular astronomy observation, to try and illustrate the work that you've been doing in terms of the calibration. So we are both interested in observations of exoplanets, in particular James Webb. Well, we are now getting an understanding of what the community are interested in, and it looks like a lot of people in the astronomy community are also very excited by the capabilities of MIRI and the MRS in particular, the spectrometer that you've been talking about. They're particularly excited about those capabilities for observing exoplanets, where here we're talking about exogas giants, so analogues of planets like our own Jupiter in our solar system. Now, what I want you to consider then is as we look out with the James Webb and we're looking at Ross 458 or whatever, GJ 504, or one of these exoplanet targets, we're looking at a bright star with an exoplanet that is separated from it on the sky by maybe an arc second or a couple of arc seconds. Okay, and we are using the MRS to observe the spectrum of that exoplanet. Now, when we look at Jupiter in our own solar system, its spectrum is characterized by a warm continuum emission that we see because it's hot, But on top of that, we see emission lines and absorption features due to molecules. There are molecular absorption bands in its atmospheric spectrum. So for the three techniques you've described, so I'm thinking of the PSF improvement, the impact of stray light, and also the fringe correction. Can you say what each of those how they would, understanding and being able to correct those three key effects would improve your spectroscopy, would improve our understanding of these exoplanets? What benefits do they give us in practice for that kind of observation?
Yes.
Does that make sense? Yeah.
Yes. So basically, compared to, if I were to first touch upon the PSF, one of the techniques, as you stated, is that we'll be subtracting the PSF of the main star in order to be left simply with an exoplanet spectrum. And so you can imagine that if you are not modeling your point spread function correctly, where I showed these diffraction patterns, these can very well be misinterpreted as the contribution of an exoplanet, or like some kind of extended emission, whilst this would not actually be the case. This would be mainly a detector feature, which needs to be well characterized. And so if we are able to do this correctly, we would be able to truly probe the properties of the exoplanet in terms of its spectral features, and not introduce some artifacts from the host star PSF. Secondly, for the stray light, this basically touches upon this a similar let's say approach. So these two things are connected. And then if I were to touch upon the fringes, as I've mentioned before, these fringes, depending on the wavelength, they have quite a large fringe peak-to-peak, let's say, amplitude. And so if you can imagine a exoplanet feature, if it's broad, let's say, or if it's very narrow, the fringes will impact the features differently. And so
okay, sorry, I'm going to burst in.
Yeah.
What I'm thinking of are, in particular, a forest of narrow spectral features. Okay.
Right. Yeah.
And so, can you think in particular? So what? Yeah.
So detecting them will be very difficult if you're not able to properly remove this effect of fringing, mainly because these narrow lines will be actually inside of your large modulation. And so if you're not able to correctly characterize it and get rid of this fringing, you are very likely to basically not detect the lines. Yeah.
You don't know if you're seeing fringes or light or spectral
Yes.
or molecules. Okay.
Yes.
Okay.
Yeah.
Yeah. No, I think that's very, very good answers. Yeah, I think that's enough for me. Thanks very much, Yannis. Thank you.
Thank you, Alistair. Professor.
Okay, thank you, Professor Glas. So then let's move to the second external member of the jury, Professor Brandl. The floor is yours.
Oh, thank you. Yes, let me start with the congratulation to a really, I think, impressive work in depth and just the amount of work, the relevance to the project, and so on. So it's really nicely written. Yeah, one gets the impression that calibration can actually be a lot of fun. It's not what everyone concludes. So this is great. But let me start with a follow-up on Alice's science questions a bit. You started out with a comparison between, I think it was the Eagle Nebula, if I'm not mistaken.
The Carina Nebula.
Where there was this nice comparison that, of course, was made by people at Space Telescope Science Institute, illustrating the knowledge that what HST people think about is infrared. So you had probably an whatever ACS image in contrast to NICMOS image, but of course what we will see with MIRI, it goes much further into the real infrared regime. And I was generally wondering, if I look at all the beautiful science areas that MIRI will see, which ones would you say benefit the most from all your work? Where is it really necessary to do so? I mean, if I just take the MIRI imager, for instance, and I look at the Eagle Nebula again, like Hubble did, I don't think it. Well, if you hadn't done this calibration, probably the image would look the same, right? But there are probably areas where it's very crucial.
Yes.
Can you elaborate on the latter?
Yes, absolutely. So part of my PhD was actually in collaboration with the Arizona University, where we looked at electronic effects that actually are applicable to both the MRS and the imager. And so several of these effects will actually have a important impact, including the nonlinearity and the RAM pull-up, pull-down, which I elaborate more in my thesis. And so these sort of effects, especially for faint sources, I think are very important, because you say that we will observe them anyway. They actually introduce important constraints on how deep you can observe, and how, since we're, as I said, interested in very distant objects, I believe, so I would like to argue that it is important to actually characterize these electronic effects both for the imager and for the MRS simultaneously.
And when you say faint sources, do you mean, say, you look at some young cluster and you have bright stars and very dim and faint ones, those, or just really just a few photons like you had at the high redshift galaxy in the middle of nowhere?
So I can give a more concrete example for one of the ERS programs that I am involved in. We have interacting binary between a Wolf-Rayet star and another massive star, and so when they come close to periastron, the winds of these two stars are colliding, and they produce intense, dust emission into the surrounding medium. And so these electronic effects I just mentioned actually are very important in order to be able to probe this dust, which is very bright in its core, but then it fades away as you go into the wings. And so there is a lot of work being put in by my colleagues to be able to really see how far we can probe this dust, in terms of faintness. So this is one concrete example that I can give.
And you think you can distinguish between the winds from the star and the stray light due to the detector?
Well, for extended sources, this should be easier to do, in the sense that we do not, for the central star, we'll be doing BSF subtraction based on a reference star observation, and then we'll be looking at the dust elsewhere. So, yes. Okay.
On, I think it was slide 26, you showed the Andromeda galaxy, and then you showed the effect, and you had two blurred, high resolution blurred image there. But it was just for illustration, right? This was not really the effect.
That is correct. It was to illustrate.
Good. Otherwise, I would be really worried now.
I made it, much worse.
Let me briefly come back to the PSF fringing. Maybe you even said it, but and I missed it. But it appears to me that first you talked about the PSF, the optical scattering, and then about the fringing, which of course requires some reflection. Aren't the two coupled in the sense that if you had no reflections, neither of these effects would appear very strongly?
That is correct.
Okay, and on slide 31, you showed the PSF in comparison. And can you bring this up again?
Yes, I can.
Maybe I missed something there.
Yeah. I just need to select the
I think
screen.
it was slide 31, where you had, in two colors, you had the line profiles overplotted.
Is this the one?
Oh, maybe it was the previous one. Maybe another one?
I can...
Yeah, this one.
Okay, yeah.
Here, the channel 3.
Yes.
I don't understand the normalization of this plot, because I would have thought the theoretical PSF goes to the maximum, but I see a red tip.
Yes. So this plot, I was not the one who produced it, but you are correct that they're not normalized to the same.
If I shift the blue curve upwards, as it should be, I believe, then of course the discrepancy to the observed one is also reduced.
Yes, but I think the two are normalized to unity.
So maybe it's just a resolution problem, a PowerPoint problem rather than a calibration problem. Yeah. Yes, let's move on to the... I have actually... Well, as I said, it's a really impressive thesis, 266 pages, and I had to read very long until I found a sentence which I think is wrong.
I'm almost sad.
And that's the one concerning the detectors on page 27, 28 in your thesis. And there you write about the blocking layer.
Yes.
that let me see, yeah, there. When the detector is operated at sufficiently low temperatures, thermally generated free charge carriers cannot penetrate the blocking layer because it lacks an impurity band, and the carriers have insufficient energy to be lifted into the conduction band. Now, if that were true, it seems like this blocking layer would be an ingenious invention to avoid any kind of dark currents.
So in
any blocking layer, you have 0 dark currents, but of course that's not really true.
Yeah. So it is, the invention of it was an ingenious way to minimize dark current, but of course you still have diffusion of electrons that can reach your pixels, and so the dark current is very, very small, but yeah, indeed, it is not 0.
Okay, so I think, okay, this is maybe a bit picky, but I think whenever you thermally excite an electron, it will be lifted to the valence band, conduction band.
Conduction band, yeah.
And the blocking layer can't do you any good. So the cooling is important to limit the number of thermally excited charge carriers. What you do have is that in order to make this detector work well with a high quantum efficiency, you use very heavy doping in the absorbing layer. And this heavy doping will lead to something like hopping, where you have the wave functions overlap. And if you then do not have a blocking layer, then you have a very high current there, which of course looks the same as a dark current. But but you have no way with the blocking layer to control the thermally excited electrons, because they're in the conduction band anyway.
I will submit an erratum to ABS.
Okay, I was just so proud that I could find something that wasn't correct, because otherwise,
this is an introduction. Yeah.
It's quite impressive. What concerning the PSF, actually, do you know if the imager, your colleagues for the imager team, have seen the same effect there? Is it quantitatively also the same?
So it is the cruciform pattern, as I mentioned before, for the IRAC, was something in the mind of my University of Arizona colleagues, and specifically the paper by András Gaspar, 2020, which I mentioned in the slide, actually models this cruciform pattern for the imager using quantum electrodynamics, and so they actually are able to improve the imager model of the PSF. However, the cruciform pattern was never considered for the MRS. We knew that we were planning to take observations of very, very bright sources to see if it is indeed there. But by investigating ground test data, I was able to actually find this similar kind of effect and actually characterize it in how it behaves spectrally as well, and how it drops off, as I showed.
And in part of the wavelengths were not Nyquist sampling the PSF anyway. I imagine that there the scientific hit is much even worse, because the detector doesn't care about the sampling, whereas if you would be oversampled by a factor of 5, the little bit of scattering probably doesn't make much difference. Is that correct?
Yes, that is correct. Yeah. In the shorter wavelengths, we are undersampled, channel 1. Yeah.
Okay, well, thank you very much.
Thank you.
Done with my questions and have.
Okay, thank you, Professor Brandl. Then let's move to the people from the Institute for Sterrenkunde. So the first one is Dr. Tkachenko. So the floor is yours for questions.
Thank you, Joris. Yannis,
hello.
Big congratulations. So excellent presentations. Thank you very much. I liked it a lot. Congratulations on your work. Yeah, so it's also impressive. It's a huge contribution to science, instrument science, but still science. And yeah, I must admit that I learned really a lot from your thesis. Yeah, so it's not really from my field, and I learned really a lot and a lot and a lot. So maybe it doesn't, talk too much about the quality of thesis by my stupidity, but that doesn't change the fact that I learned a lot. And so Professor Brando just mentioned that you have 266 pages in your thesis, right? So I found a copy of thesis in my mailbox today, and it has 239 pages in it. So I appreciate that you cut 27 pages of difficult stuff for me. Yeah? So a special edition for Andrew. Thank you very much.
I need to talk to the print shop. Something went wrong there.
So my question, so actually a funny question then would be, and you can answer it later, where are the rest 27 pages? What is in there?
I'll come to your office. Yeah.
A second question, very general and perhaps an easy one. Can you just, tell me what would be the instrument of your dream? So if I would have given you $1 billion, what would you build and what would you observe?
Yes, thanks for the question. Admittedly, I think the MIRI design is very ingenious, so I wouldn't go looking too far from there. However, as I mentioned, for 4 years I've been dealing with this detector scattering, and so if I were to give you the ideal sort of detector or ideal properties, it would be twofold. So first of all would be the in terms of the anti-reflection coating, if there was some sort of let's say material that would basically allow your detectors to not produce any sort of coherent reflections, I think that would be absolutely amazing. However, there's also an issue with the fact that our Echelle gratings, or sorry, diffraction gratings, I should say, they actually provide us with a limited spectral resolution. What that means is that whenever you're trying to get the properties of the fringes out, because you are sampling your fringes in a very rough manner because you're at high spectral orders, it's actually very difficult to do that. You have very limited information. So if you were to have, let's say, a high resolution spectrometer, you could actually use the fringes to your advantage to improve, for instance, the wavelength calibration. And so that is part of my work. If we are able to understand really how the fringes behave, we would then be able to do interesting science with them, because then you could see potential wavelength shifts with respect to these references. And so those are the two answers I would give. Okay,
excellent. Thank you. So actually, $1 billion might not be enough. But okay. And in the meantime, Professor Brando answered my first question. So apparently I have also issues with basic mathematics. So yeah, so the nominal page 1 actually appears on page 25 of your thesis. So sorry for that.
Okay.
All right. So then, hopefully I'll save here some time for my colleagues. So that's all on my side. Thank you.
Thanks, Andrew.
Okay, thanks, Andrew. So then let's move on to Dr. Royer. The floor is yours for questions.
Hi, Yannis. So I would like also to congratulate you for the amount, but especially the quality of the work you've done, and the approach that you have taken to problems, which is that you don't take anything for granted. And that is a very, very important aspect of the work, and it has proven that it pays when you do that. So it's hard work when you want to dig into the problems up to the bottom, but you've shown that that's what you do, and it really pays off, and so that is really appreciated. For the quantity also, I have to say to the general public that in these 266 pages there is more than what you have presented. You have really basically touched upon all aspects of the thesis. I think you recently deserve more congratulations for obtaining congratulations from Andrew. On top of that, I want to mention that it was a great pleasure to work with you. I hope that it was a shared feeling. I had good fun, at least. It was, So I would have a question, which is a double question, and which goes about more lessons learned, looking in the two directions of the arrow of time, I would say. So maybe the future first. What do you think will be the biggest challenge that we will be facing in commissioning in terms of calibration?
Right. So there are, as I stated in my thesis, there are a number of aspects that still remain to be solved. One of them is related to the electronics. So we have several crosstalk sources which we are still not able to properly model, and they impact our ramps specifically for fainter observations. And so this, I believe, is something that we need to get a better handle on. And secondly, of course, everything always comes back to the fringes. So it would be great, based on the effort that I've made, to be able to simulate a sort of static fringe map for different types of sources and detector illuminations. So this is something that is in the work plan. However, and it will contribute significantly to all MRS observations, regardless of whether you have point source data or semi-extended source data, and I believe will be a huge contribution to the astronomical community. So I believe the effort should be on that, and the outlook should always be on these two aspects.
In terms of crosstalk, you refer to the pull-up, pull-down effect, especially
Yes.
for the MRS.
Yes.
What would be the approach to correct that effect? Because in one of the directions, it's really challenging. So which kind of perspective do you have there?
Right. So the main thing, of course, the more data you have, the better you know how it behaves. So of course, our de facto, over time, our understanding of these effects will improve just because of the amount of data that we get in. However, as you correctly stated, we have one direction, which is in the spectral direction, where due to the, let's say, the fact that you're looking at different wavelengths, but you have signal in all of them, so it's hard to decouple. One of the main considerations here is exactly how much will the pull-up, pull-down affect them, because the only way you can get this effect is when you have large variations in voltage reading between pixels. And so what that means is that if you do not have pixels in the spectral direction, where in one pixel you measure a very high flux, for instance, in an emission line, compared to a very low continuum, if you have simply just a smoothly varying continuum, then you will not actually detect this effect, or this effect will not impact as hard. And so we need to differentiate between different science cases of the MRS, such as the ones I just stated, between bright emission lines on a low continuum and other cases. So I think that's also an activity that needs to be done.
Okay. Then maybe the going back in time for the lessons learned. So you mentioned the importance of the flight model test data. And of course, so this is the workhorse for every instrument, the FM data set. And I would like to ask you a twofold question again on: are there data there in that data set that you have been using that have really been instrumental in solving some effects and that had not been acquired with this goal? And in the other direction, are there data that you actually would have liked to have at hand when you were just, okay, this effect would really benefit if we would be looking at this, but you did not have at hand?
Right. Thank you. So basically, the two aspects, I need to state that for point source fringes, which was a big part of my work, the FM test campaign point source observations were actually quite faint. And so because of that, you could not get actual high signal to noise ratio to really well characterize this effect into the wings. And so that was something which was really nice, which we used when we used the CV data. But in the same breath, the CV data only gave significant signal to noise ratio in the band 1A, And as you know, this is just 1 out of 12 bands. And so one thing that was missing there, which could have potentially helped with characterizing this effect in all the bands of the MRS, would have been somehow bright point source observations in the full wavelength range.
Okay.
Yeah, that is an important example.
Thank you. Thank you. That will be it. Yeah, thanks.
Okay, thank you. Then we move to Professor Sana. The floor is yours.
My microphone was hidden at the bottom of the window. All right.
I can hear you. Yeah.
Perfect. So yeah, definitely a big congratulations to the achievement that you've reached to deliver not only a beautiful book but also of excellent quality. As this has already been mentioned by a few of my colleagues. Because I am the fourth, fifth person to ask questions, actually a number of my questions have already been asked by my colleagues, and I would like to request that the next time you do a PhD defense, I will be moved up among the people asking questions. But I still have two to ask. So the first one is on the science case, one of the one that you mentioned at the beginning, where James Webb is going to peer further or deeper in the history of the universe than any other observatory. And if you look at the horizontal axis of that plot, you'll see that basically we have already observations that are covering the first 10, 12 billion years of time. So why is it really important to cover the last few hundreds of millions of years? Right. The first few % of the life of the universe.
Yeah. So one thing is that we have not actually gone as far back as looking at the formation of the first stars and the first galaxies. So this is an important missing part of the timeline. And so James will be contributing to that aspect, where the first, after the reionization period, as was mentioned in that plot, you got the first conglomerations of dust that formed the first stars. And so this is something that James will be contributing to.
But what would James Webb actually observe? Is it really the first stars that it will observe, or?
The first galaxies is definitely on the research plan. And so those are, of course, very low metallicity galaxies. And so we want to really see basically how they're in terms of their spectra, what sort of features they contain.
And what are you expecting that it will contain? What will it reveal to you? So
of course the metallicity is, as I mentioned, one of them. But we want to see exactly how, if we are to combine all of the information. So we don't only look at the very start, but we also look at how the evolution happened. And so we want to complete the picture, to go from to see how the galaxies evolve, and how from mergers you can get the galaxies of today. So it's a global perspective in that sense.
All right, thank you. The second question is more technical. It relates to the stray light.
Yeah.
And the fact that at some point you argued, that's on page 96, but you argued that the stray light should basically not be subtracted from the data.
Yes.
That's yeah. Can you walk me again through why this is the case, that you rather not do that? Because some point along the reasoning I was lost.
Yes. So one of the main things I need to state is the fact that now that we have more information about how this effect manifests, the very first thing that we should do is really try to see if we are understanding this effect correctly and if we're modeling it correctly. So as I stated in that subchapter in my thesis, unfortunately, we were dealing with certain issues where, because of this broader PSF, when we were using out-of-slice pixels, we got artifacts due to the interpolation methods that we were using. And so when I say that we should not be subtracting, first of all, in the first step, we should understand how this strategy manifests based on this new, let's say, information, and then see exactly if the light is still coherent. So if you're still holding on to your spectral information, where the correct thing is to subtract it or to actually implement it in your PSF model. And then when you do PSF subtraction or convolution with your scene illumination, see which method is actually better at representing this effect and correctly taking into account.
So if I do understand you correctly, your argument is relying on the fact that this stray light is not actually stray light, so like in the sense of diffuse light or reflected light on different pieces of the optics, for example.
That is
it's an integrated part of the way the instrument is, or not the instrument, the detector is reacting. So it's actually a part of the PSF.
Yes.
All right.
That is good.
I'm just looking at the time. Chairman, do we still have time for one more question, or is it time to move on?
I think you have time for one more question if you're...
All right. So I want to peer again in towards the future. So you know that James Webb has been the massive endeavor of the last 20 years in terms of space instrumentation. What would you have learned from James Webb that you could apply to the future next big step that could be the Louvois Observatory, for example?
Yes, there's the Louvois, but there's also the ELT METIS. As you know, we are very involved at KU Leuven. So these sort of instruments are very much considering a similar kind of instrumentation in terms of the techniques used. So, for instance, integral field spectroscopy is very much emerging sort of way to observe the sky and get both spatial information and spectral information. And so in that respect, I believe that the lessons learned from MIRI can very much be applied to the instruments of, for instance, METIS, which also will have an integral field spectrograph, but also the Louvois, which from the top of my head, I don't know if the latest design contains a IFU, but I think if they were to be considered, they will definitely use the knowledge gained from MIRI in their design considerations.
Well, that's probably a correct statement, but that's a very vague statement, at least right. Vaguer than what I would like to hear from you. So what specifically would you think would be some of those lessons?
So for instance, depending on the detectors that they decide to use, you can expect to see certain systematic effects, including the fringing. And if you were to then also look at the type of electronics and electronic effects, because the ramp pull-up, pull-down effect, for instance, that I mentioned in my thesis, it was also observed in the IRAC data. And so you can see this sort of like heritage where, in a negative sense, where you see that somehow these kind of effects like translate over time and we still don't have ways to tackle them. And so these are two real issues that we're facing, and we need to have a better handle on them in the future.
So in terms of Louvois, as far as I'm aware, Louvois doesn't have mid-infrared capabilities. At least it's not in the plan. It's really UV optical and near-infrared, in a sense more like HST. Would some of those lessons also apply for Louvois?
So as I showed you for the Hubble Space Telescope, the STIS spectrograph covers from 0.7 micron, at least that part, which is in the near infrared. And so an extra consideration is the fact that they use CCDs on that instrument and not silicon arsenic IBC detectors. And so in that respect, I do see a scenario where the same effects that were discussed in this work are very much manifesting in the near infrared, at least. Yeah.
All right. Thank you very much.
Thanks.
Thank you, Professor Sana. So then before going to the supervisors, I think I was also chosen to be in your jury as a solid state physicist, so I can also ask some questions. But perhaps already to the audience, let's say there is also questions possibility for the audience. If you have a question, I think now is the moment to put it in the chat already, so we can be prepared for that. But okay, so Yannis, let's first, as well as many of the colleagues here did, congratulate you as an outsider. I think it was something we discussed in the preliminary defense. You gave a very instructive presentation, which is nice, and improved the manuscript were requested. So I really liked your efforts, and it was already, as stated by many of the colleagues, it was already extensive, but I think you made it even more bulky. But I think it was definitely for the good. So for me, to wrap up, it was a pleasure as an external reader to do this. So let me ask you a few questions. Yeah. I hear an echo somewhere, but okay, whatever. So, because this was also stated by, I don't know exactly whom, calibration is fun, no? But okay, that's, I'm not aware, let's say, of all this expertise, but probably calibration is one of his expertise. Can you, as a PhD student, and for probably people in the audience, say like, look, do you regret to primarily work on calibration? Or yeah, can you comment on that? Or do you say no? I mean,
absolutely not. I think it is something that perhaps I have mentioned this, but as my bachelor degree, I did aerospace engineering, and this sort of mentality of having the pieces fit is something that is very much at the forefront of my motivation when I work. And so when you give me a sort of a problem where you know that you can use the tools at hand to really make things, or things that seems disjointed somehow follow the same, let's say, line of operation, then I very much enjoy this. And so although my PhD was supposed to be 2 years of instrumentation and 2 years of exoplanet science, as it were, the opportunity that I was given to work on very challenging problems, which I of course go in depth in my thesis, was one that I welcomed, and it provided me some leeway to really like invest time in these problems, which would otherwise be shoved under the rug, so to speak, when the time came to do the commissioning phase. So.
Then perhaps to say it's thank you. So a technical question. I think it was related to slide 49. No, I'm quite sure if I'm correct.
Would you like me to share? Yes.
Yeah, just to be sure that I'm talking nonsense.
2 seconds. Yeah.
Because I think you also mentioned it. Let's say even you see the fringes at high wavelengths. No. Let's hope I followed your presentation.
Is this the one?
Yeah, but no 49. What was 49? I think there. No. So this was then the explanation. But my question is indeed, the fringes survive very far. While if I look to your thesis, you see that this is a technical question, but I mean, I'm here for curiosity. You see that the absorbed intensity is 100%. Why then you still, with your explanation, on slide 49? I mean, how is this compatible with your explanation? Because you need, let's say, interference back and forth. So can you comment? Sorry.
Yes. So basically, you get interference whenever, or reflections whenever the index of refraction between two materials jumps. And so one of the plots that you can find in my thesis in chapter 7 shows that the index of refraction of the buried contact due to the doping concentration in this one actually changes drastically towards the longer wavelengths. And so because of that, because of this difference in refractive index, so specific, I'll point you to figure 6.14 in my thesis. So because of that, this monotonic change in the refractive index of the buried contact induces these reflections at the buried contact, and so this explains the fringes at the longer wavelengths.
Okay. Then let's say, thanks for that. But then let's say I have a question. Let's say this telescope, and it's already a long endeavor to launch it, etc. But how old are these detectors? That perhaps like a strange question. Let's say the detectors. Let's say they are developed, the hardware. Then let's say at what time in?
Well, that was. I'll stop sharing my screen.
Always in your thesis, but.
Yeah. So those were developed at the very start. So already before 2008. So it's more than what is it, like 20 years
okay,
ago?
I was expecting that answer, but isn't that it a surprise that you say the machine is perfect? If I would give you like an awful amount of money, let's say if I would give you a mobile phone and let's say a smartphone from 2008, you would be very disappointed. So I was, let's say, a bit surprised on your question. So, and as a solid state physics, can you comment, what isn't there anything which can be better on these detectors? So is the detector business dead then, let's say? Can you comment what you would say would be an improvement, or is there really no improvement anymore?
So no, that is absolutely not true. Of course, the moment we've equipped these detectors and went through the test campaigns, it became, let's say, we ran with them. So at some point when you've assembled the whole thing, you can no longer disassemble it.
But if you can dream then, and you have all the money, and you can start from scratch, and you can spend the time of the next PhD student for the 20 years. I mean, what would you then do? What would you learn and make different, let's say? If you would have been there now, go back in time and say, look, make the detectors like this, because this will ruin the PhD students coming after the development.
So, of course, I'm not in the, I'm getting an echo. I'm not in the detector manufacturing business, but the main thing that I would, of course, look at is, as I mentioned in my presentation, exactly how different types of anti-reflection coatings can improve the performance of these detectors, and that's a very important issue that needs to be brought up. The other issue is, of course, these detectors were developed in a sort of classified sort of environment. So we've been working in a bit of a, let's say, not completely blind, but a lot of the findings in this work were based on the data, and necessarily so. And so the combination of these two things, of course, any information that you get on these detectors is useful. But yeah, so the lessons learned can definitely be used to also inform when you look for a new detector. Be sure you ask the right questions.
Thank you. Thank you. So then I will leave the floor here. I will switch to your supervisors if they have any questions. So Professor Walkes, you have a question?
Thank you.
Comment?
I have a question, yes. But first I would say that the real supervisor is Bart. So I was honored to be formally your supervisor for the academic reasons which imply this to some extent, okay? But it's also true that, I was the first one involved with MIRI, in fact, at the Institute, and in this framework, I want to congratulate you and to thank you for the beautiful work you did. Maybe we can say a few words later as well. But I want to congratulate you with an excellent work, and so very good results, very nice manuscript, and also today a very nice presentation.
Thank you.
And what I have already said in the preliminary defense, after the preliminary defense, I want to repeat here, but in front of a broader public, is that I very much appreciated the way you did the job. It was a very scientific attitude you always developed. So, well, we have been discussing about the pleasures of calibration, but, well, your goal was not so much to produce a recipe and to offer to scientists then so that they had the impression that their spectra were nicely smooth. No, it was to understand in a very scientific way. So it was instrument science. It was to understand what was behind all these phenomena you saw. And well, I think everyone feels that you have been extremely successful. And that was very nicely said, in fact, in your presentation, because you have, to some extent, the common cause, which is this photon scattering, which helps you to explain all these things. So well, you have, in a sense, produced a theory of all these things, which may work. And well, on the 6th floor of our institute, where the theoretical physicists are, there is a very nice poster telling there is nothing more practical than a good theory. And I think that's a nice way of putting things. But then, indeed, so it was all designed for the work for MIRI, but you mentioned, and I come a little bit back to the last question addressed by Hugues, you mentioned that fringing appears everywhere, also then that these point spread functions with broad wings are not unique to MIRI, and so forth, and you had a kind of explanation for all of them. But then, of course, the question arises, to what extent is what you've done restricted to MIRI only, or does it also contain lessons and help for others? Huh? So, certainly the details of the detectors must, for MIRI, are not the same as elsewhere, but were you able, or are you able to isolate a kind of general guiding lines, or these are the new things which everyone involved in this kind of business for any instrument should look at? And you mentioned METIS, the instrument, which in a sense is the MIRI for the ELT, although I don't know whether, or PI for METIS, Bernard Brandl will exactly define it like that. And other instruments as well. LUVOIR has been mentioned. So to some extent, that part of my question has already been answered, although I would like to know to what extent your theory is generally accepted by these people as being the starting point for what they will investigate. But then, I also, and that it may be a naive question, but when you showed the Spitzer results, is there any way to go back to the original data there and to apply your understanding of what really happened in these detectors, and to really reanalyze the raw Spitzer data and come out with better Spitzer results even today? That's my question.
Yes, thank you for your question. So one thing I should mention is that, of course, Spitzer has a very large catalog of data, and so I believe that in terms of their approach to resolving the fringe patterns, they've had, let's say, a lot of time to produce dedicated sort of measurements for different sort of observations. And so in that respect, I believe that their approach is more empirical in a sense compared to theoretical. The paper that I referred to, the Elliott-Malamuth et al. Paper, tried to model the fringes, as it were. However, the approach, the modeling approach, still was not sort of folding in this issue of how the pixel illumination translates into the different behavior of the fringes. And so that my work would then come as an addendum to the work of Elliott-Malamuth, to see if we can actually improve, let's say, the theoretical model that was described before. And then more importantly, we need to see whether how much this implementation of the theory can improve in the spectral information that you get out. So these two questions are very much interesting, and I would love to look at that. But I believe that we can definitely produce a better theoretical model. Now, whether, given all this empirical data that Spitzer has gathered over the years, we can show up there and say that our solution works better than an empirical solution, that is a difficult thing to say, but it's still an interesting question, and I would love to try it.
Okay, thank you.
Yeah,
that's
thanks.
That's the only question I had.
Thank you.
Okay, thank you. So then let's move to the final person, Dr. Van den Bussen. The floor is yours.
Thank you, Chairman. So, Yannis, I will leave the congratulations for later. Let's not be too
premature.
Congratulations. I have one question left, and it's a question I got myself this morning. So in the Ariel space mission, it's near-infrared spectrometer for transit spectroscopy of exoplanets. The question is, should we spend 2 million on an internal calibration source or not? Mm-hmm. And the calibration source, which currently is the baseline, is a filament, very much like the filament calibration source we have on MIRI. What is your opinion?
Right. So, of course, Ariel will be doing low-resolution spectroscopy, and in that respect, in terms of getting information about the fringe patterns and how these actually modulate it, is very difficult to do. Now, for the internal calibration source has more uses than just characterizing the fringing. And of course, you can look at how the detector response changes over time. And I think that is worth investing in. And also you can use this to, as I stated, check the, let's say, the spectral response function of your instruments between on-ground testing and in-flight testing. And so I think that you should definitely have an onboard calibration source. Yes.
Definitely. Okay.
Yes.
That was the only question I had, Chairman.
Okay, thank you. So then there is perhaps one short, let's say, explanation from my side. So it was already stated by some members, there was already the first defense where there was a much more extended and technical discussion. So now is more, let's say, more broader questions as seen here. But this also makes room for questions from the audience. So with that, let's say the floor is now for the audience. Ask the pertinent questions you always wanted to ask to Yannis about his work, of course.
If there are no questions, I'm going to assume it was perfectly clear.
It was perfectly clear, every slide. I will wait for a few more moments, but if not... Okay, I think there are no questions. Correct me if I'm wrong. Also, the members of the jury, I think, post all questions. So then I hear close, let's say, the first part of the session. The jury will go for a deliberation, but all the other people should stay here, but we will come back in a few moments. Thank you and see you soon.
Thanks.
I see everyone is online, but Christoffel is not in front, so let's wait for a second. Okay, everyone hears me properly, then let's start again with the second part after the deliberation. So, ladies and gentlemen, dear colleagues, I will now proclaim the results of the deliberation by the examination committee appointed for the doctoral degree in science, astronomy and astrophysics. Mr. Yannis Alexandros Argyriou Tsikrikonis has presented to the faculty his PhD thesis on the topic calibration of the MIRI instrument on board the James Webb Space Telescope and MIRI exoplanet spectroscopy, in partial fulfillment of the requirements for the PhD in science, astronomy and astrophysics, and he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, confer upon Mr. Yannis Alexandros Argyriou Tsikrikonis the degree of Doctor in Science, Astronomy and Astrophysics. I hereby close the session, and I want to congratulate you by at least giving a short applause, Yannis. So congratulations. It's a pity we don't have a reception, but okay. So I will give the floor to your supervisor, Bart. The floor is yours.
Thank you, Mr. Chairman. So, Dr. Argyriou, dear Yannis, it's a pleasure to be the first to address you with your academic title of Doctor in Philosophy, PhD in Astronomy and Astrophysics. So, where shall I start? Well, in a summary, I have truly enjoyed to work with you. You are an intelligent man, well organized. You show an honest scientific attitude. Several people have said that already before. You also have a great sense of humor, but especially you also have a great sense of empathy. And that is actually a rare combination to find in one person. So that is a thing I certainly have been appreciating a lot working with you in the last years. Time to for some nostalgia. Eh? So when you started your PhD, we wanted to focus on methods for optimal extraction of spectra from MIRI medium resolution spectrometer measurements. But very soon you were hitting the limits of what you could achieve, because any further improvement was limited by the accuracy of existing corrections. For a plethora of instrumental effects, you've shown a lot of them today in your presentation. And at that time, I warned you that tackling all of them was impossible. But when I now look at your thesis, it's actually clear that I was wrong, because you did manage to go in depth into the physics of the MIRI instrument in a variety of aspects. And you made a substantial contribution to the calibration of the instrument in all major areas. And if you look at the first programs that we are going to execute with JWST, the early release signs and the guaranteed time observations, the MIRI instrument, and especially the medium resolution spectrometer, is one of the most popular instruments on the observatory. And so without your work, the majority of key observations that will be done with JWST would never be able to achieve the accuracies we need for those measurements. Now, you have been working with our MIRI group here in Leuven, and I especially want to mention there Pierre Royer, of course, because he's been extremely helpful in collaborating with you, providing feedback on a large part of your thesis work on the detectors. He's been your sparring partner in many aspects there, but you've also been, of course, working with many colleagues around the world in the MIRI partner institutes, also at the Space Telescope Science Institute in Baltimore. You learned a lot from them, but you also helped them a lot to understand and correct MIRI instrumental effects in the data even better than what was possible before. And for people listening here, maybe you know, maybe you don't know, but answering a question from Yannis is actually never a waste of time, because once you explain something to him, not very often, a few days later, you get an email back with a Python notebook, transforming your fuzzy ideas or your fuzzy understanding of what you explained into well explained and mathematically sound demonstration with beautiful plots and simulations that actually show exactly what we've discussed. So today, it's actually for Professor Christoffel Walkens, the defense of the last PhD student that he supervised as a promoter before his retirement. So it's also, in that respect, a remarkable day. And Christoffel started in Leuven the participation in developing astronomical instruments, first ground-based with the Mercator telescope, with the collaboration with Geneva and involving all the politics that the complexity of the Belgian state has to actually build an observatory in La Palma. And now, 30 years later, we see it's a very powerful facility that we're enhancing with new instruments as we speak. 25 years ago, he also started to be involved with space missions, first in the Infrared Space Observatory, then in collaboration with the Space Research Organization in the Netherlands and the Max Planck Institute of Extraterrestrische Physiek in Munich. And since then, we have been contributing in a very meaningful way, in our own way here in Leuven, to several exciting space mission ground instruments. And now we're also taking the lead for several of these instruments projects. So I believe that for Christoffel, the high quality of your instrumentation thesis is, in some sense, the cherry on the cake, maybe, and the recognition also of what he has achieved in initiating instrumentation projects in Leuven. So actually, I would like to pass for a short. I want the word back, Christoffel. Yeah. But I think it's the right moment to pass the word to Christoffel to say a few words here.
Okay. Thank you very much, Bart. But I want to congratulate you as well of the whole story which you've been unfolding. You were an important part. But before embarking on that, having listened to our chairman pronouncing your name and seeing you laughing a little bit, you knew. I think you may remember that as chair of the examination committee for a Master of Astronomy and Astrophysics, I used to do the proclamations without a piece of paper, knowing the.
I will never forget that, Christoffel.
By heart. Yeah. Well, not just to do a kind of performance, but to show that our students are our partners in science, and really we live with them, our master students for 2 years, and then having to read their name is a little bit strange sometimes, from the moment you do not have too many, and that the names are not too difficult. And I remember
You'll remember me.
I was nervous, but I managed. But let's come to what Bart has introduced. When we got involved into MIRI, in fact, the project was already going on for some time, but there was some crisis because one of the international partners could not really commit itself as it had wanted before. And Belgium was found as a replacement. And I was asked to be the PI, co-PI for Belgium then. And that was at a time that we were really very much involved in Herschel as well. So it was not so sure how we could manage that. With Prodex, and they needed me as a PI, but it was for them the hardware investment was considered very important, and there is another institute in Belgium where that is done, and they do it very well, and we have very good collaborations. But and then I remember having said then, I would like to be this co-PI here, but that means also that there will be a role for our institute, because what Bart has a little bit described is an important aspect of the institute on which we have relied indeed very much in order to increase our scope. So the instrumentation group, which of course is based on an external funding by Prodex and so forth, is key in the institute, and the involvement in MIRI was to some extent also a way for me to guaranteeing the future a little bit. So it was in the first place, yes, more on building on the expertise which had been developed with ISO and then later Herschel and so forth, and by Bart and Pierre and others who you know very well. So it's very important that we perform there very well, and I think we have done so. And if I say we have done so, then I can say you have done so. You and Bart and Pierre and all the others, and I'm very happy to have been at the start of that a little bit, and I am very proud of what has been achieved, because, as I said, what you have done is very really a kind of cherry on the cake, and it's the colleagues from abroad here who are also members of the jury, I think they agree that what you've done is excellent work, and it has really been a big contribution to the good reputation of our institute. And as a formal responsible about that, I want in the first place to congratulate and to thank you for that, and to wish you to build further on that. And I hope that you are I don't know what your plans are for the close future, but by all means, you're always welcome, and we wish you all the best. And again, thank you very much, and congratulations once more.
Thank you. Thank you so much, Christopher.
So I was indeed not incorrect that Christopher was not entirely unhappy with the last PhD student he's co-supervised. So, okay. So this PhD, I think it's just the first milestone of a long career that is going to be full of exciting achievements that will move stones in the big river of astronomical instrumentation and eventually alter its stream. And so I'm picturing Dr. Argyriou a few years from now, listening to his PhD students who are complaining how demanding a PhD project is. And then I picture you will go like, you know, kids, back in those days when I was a PhD student, because indeed the trail of your PhD was not exactly paved with rose petals. Huh? So I think that actually as a toddler, you played hide and seek in an ancient Greek temple, and then you upset a grumpy ancient Greek god, who then decided that, well, this Leuven PhD time, it's payback time, because indeed, there were a couple of obstacles on your road. In the beginning, these obstacles on your PhD trail, they were often created by me. I admit that was rather inconvenient when I booked a hotel room for you in Paris on the correct day and the correct month, but the wrong year. And we kind of sorted that out. But you also helped yourself in avoiding a boring PhD life in the beginning. I promised not to tell anyone, so I will also not elaborate on that, how exactly you discovered that Thalys trains have automatic taps on the washing basins after you put an open suitcase below one. Anyway, but these were only minor testings of this grumpy Greek god that you upset as a toddler, I think, because then it was time for the serious stuff, obviously. So in the summer of 2017, we were testing the James Webb Space Telescope, the telescope and the instruments in a huge space simulator in Houston in Texas. And a few days before you were scheduled to travel to Houston, I was already back and you were about to leave. And then this grumpy Greek god made Hurricane Harvey come to land. And you were waiting for days and days in Schiphol Airport, eager to catch the first plane into the airport of Houston. So I think you were on one of the first airplanes to land in Houston after the storm passed and then the flooding had retired a bit. And so you were one of the first team members to get in the Johnson Space Center. I think many of our MIRI colleagues who were at that time there were relieved because they had been stuck already in the center, running the tests and then sleeping on mattresses in meeting rooms on site and surviving on limited provision of toilet paper and unlimited supplies of canned beans. So it must have been quite an experience. Anyway, but and then, well, of course, the last year of your PhD, you're basically locked down in your apartment while they were also reconstructing it. And when the coronavirus arrived, the Alma restaurant was closed, so no moussaka for lunch. Must have been very bad. The good thing is probably there was not much else to do than to write a great thesis text. And now we all benefit from that because it will serve as a reference for many colleagues worldwide who will try to understand the instrument effects in the James Webb Space Telescope instrument. Unfortunately, still today, we are a bit limited in the grandeur that a PhD ceremony typically deserves. And also later tonight, I think the post-event defense extravaganzas will have to be a bit less legendary than we all would like them to be. So I propose a new ceremony. Yeah? In some circles, married couples renew their wedding vows a few years after their wedding. So let's have a PhD renewal ceremony after the JWST commissioning. We get the jury over to Leuven. You present your thesis work, at least the few things that have not been proven wrong by then. And then we grill you with some questions, and later we grill the souvlakis. We wash them away with Retsina while we hug you without a mouth mask, and we're dancing a sirtaki. So that is the plan to compensate for what we cannot do today due to the COVID situation.
That would be amazing.
Okay. But okay, there were these testing times. Of course, there were also a few days without too much trouble, and I talked to you about you as a fine colleague in the large international collaboration, but also in our institute, you were just more than just a fine colleague. For the master students, you were the ombudsman for years. And I'm quite sure that you really made a difference for many students and you helped them through their undergraduate studies in a very meaningful way. In the Institute, you were the one who joined even the most obscure sports initiatives. You organized the Institute's Uitje, you decorated Christmas trees, motivated your fellow PhD students in GATKIP meetings, and I think you were not only a very fine colleague, but also a good friend for many of the people in the Institute. And I want to thank you for that. At this point, I would also like to extend my congratulations to your family, actually. Today, you have every reason to be proud of your son, your brother. If today Yannis has been awarded the highest academic degree, it's not only thanks to how clever he is, but also thanks to the person he is. And you gave him the warm nest and opportunities that actually helped him to get where he is right now. So I want to thank you for that, and also my congratulations to you. So, Yannis, I would like to finish by offering you a small gift. And that will hopefully be a good memory of this day. It's today is the day that you finished your marathon, running a marathon through the PhD desert, thirsty for knowledge, running to that fuzzy oasis on the horizon at a steady pace. So I think I have an appropriate small present for that allegory. So you are in the meeting room at the Institute. So behind the television screen in the corner, there is a white box that with some blue tape on it that has been recycled from a COVID protection.
Should I go get it?
Exam. You can get the box.
Yeah, give me 1 second. Sorry, cables.
Yes.
Yeah, got it.
Yeah, in the box, there's a parcel. It's like a box.
Okay, so I don't need the box. Let's see. It's not fragile, I suppose. It feels.
It's not fragile.
Oh my God! It's a camel bag for running, with the Mercator logo on it, and that is also the logo of the IVS. Thank you so much.
So congratulations! I hope you will. This will make your running performance exactly. You're ready to go. So congratulations again, Yannis. I'm looking forward to see the first to see JWST produce unprecedented spectra that are well calibrated thanks to you after we launch later this year, and then I'm looking forward on to a bright future with exciting collaborations, hopefully with you, when you are building new generations of space instruments. Thanks.
Thank you so much, Bart. Thanks. So, do I have the word, or I would also, yes.
You still have people watching on YouTube, so
yeah, because I have to entertain. So thank you so much, Bart, and thank you, Christoffel, and thank you to all the members of the jury for helping me in this final phase of my PhD. It was an absolute joy throughout, and I was very very happy to be able to have you on board for this final phase. But as you know, as was mentioned repeatedly, this defense is slightly different in the sense that we cannot all be together. And so I racked my head to find a way to get us all together in some way. And so with that, I think if you will allow me to share my screen one last time with all of you, I would like to share a few memories from my long path to get to this point. So first of all, I would like to thank Bart, who in November 2016 in the airport of Zurich, he had the clever idea of taking a photo of me drinking cold water after eating fondue, which, as you know, is the worst idea ever, because then I had to justify the extra weight to the airplane, let's say, gate. And honestly, I don't know what I was thinking. But this memory for me is memorable, as it was one of the first times I got to sit down with Bart around a nice meal. Secondly, I would like to thank Escape Room Leuven for letting us rob a bank. Honestly, I think legend has it that the mallet with the money is still somewhere at IVS, so people can start looking for the scavenging results. Then I would like to thank Libramont for answering the questions of how many people does it take to bring down one IVSer. So help me do the counting. It was absolutely amazing. Then I would like to thank the Johnson Space Center for letting us use their main room after the side room had gotten flooded. As you remember, Alistair and Bart and Pierre the side room where there were still people in there, but they had put drapes to keep the water from spilling all over the place. So this was me and Misty could just enjoy the main room while staying dry. Then afterwards, I would like to thank Wim de Mested for showing me Apollo's massive rocket. The Apollo's mission massive rocket. Then I would like to thank Parish Weather for not raining on our heads when we went to celebrate the defense of one of our colleagues, and at least one of us was well prepared for such a scenario, and with the effort of all of my IVS colleagues who got his hat, PhD hat, all the way intact. That is one memorable moment for me as well. I would like to thank Saskia Prince in La Palma for always giving me privileged access to the Mercator Wi-Fi so that other students could just crawl their way through the web, and also for always making me jealous of her Santan. Then I would like to thank the Nair Sports Center for never calling the police on us whenever we would go out half nude playing beach volleyball. Honestly, I think, guys, we should have kept the net up in the background. It would have been made for a better justification. Then I would like to thank fingers, apparently, because they always grow when you least expect them to. Honestly, Keto, I need to get back on you for that. Then I would like to thank the University Trail for reminding us to take time off of science. It was an amazing time, and unfortunately, I'm scared to admit that afterwards we just all got back to work. Then I would like to thank rocks for existing, apparently. Gravity is so strange here. That's a reference for Andrew. Then I would like to thank Vlimmeren Volleyball Club for letting us join with our inner tattoo artists. Vlimmeren, that's a reference for Robin. Then I would like to thank my nieces, Anaïs and Viviane, for making me feel glamorous on a few days per year. So, bisous les filles, je vous aime. I would like to also thank Astier, Gîte de Table, for letting us borrow their cat to beautify our IVS portrait, and only calling the police on us once. Then I would like to, never mind. Then I would like to thank Philippides for boosting me and Sarah's ego after coming out alive from a marathon. Of course, you can see that this photo was taken before the marathon. I shall not show you one after. I would like to thank Stella Artois for their naivety, teaching grown men to pour themselves beer. There was no stopping us after that. Then I would like to thank Luca for holding onto the floor. I really don't know what was wrong with the tilt in this photo, man. I should improve my selfie taking skills. And then one before last, I would like to thank this little guy for staying strong and making it all the way to this day. I mentioned at the very beginning that I've been working in the sandbox on the shoulder of giants. I just didn't know how early I started doing that. And so finally, I would like to thank everybody for making me even crazier and a better version of myself. And, the years got nothing on you when you have the right people surrounding you. So stay strong, stay safe, and may we meet again.
Congratulations to you once more.
Thank you.
There's only Joris and me to applaud, but I think everybody there is.
Thanks a lot.
I'll pass by the corridor to give your official document at least.
Thank you.
Okay.
Thanks so much.
I will leave the studio here.
Bye.